Today, we're diving into something pretty amazing. We're going to look at how a huge environmental problem, I'm talking about oil spills, is being tackled. But not out on the ocean. Nope. It's happening inside a computer, all thanks to some incredible digital engineering.
Okay, so take a look at this. On the left, that's the old way. A bunch of people literally wrestling with this heavy, awkward equipment. Now look to the right. That's the proposed fix. One person, a custom machine, and a whole lot less backbreaking work. This one picture, it really tells the whole story, doesn't it? The problem and the promise of a much, much smarter way to do things.
All right, so let's set the scene here. We're talking about the world of oil spill containment. It's high-stakes stuff. You got to get equipment out there fast, and you have to do it safely. But here's the kicker. The gear itself is a massive physical problem.
How big of a problem? We're talking about 120 kilograms. That's, what, about 265 pounds? Now, just try to imagine moving that section by section, probably on a rocking boat or a slippery dock. Yeah, that's the challenge these teams are up against every single time they deploy one of these oil booms.
And as you can probably guess, trying to manhandle that kind of weight has some pretty serious consequences. For one, you get a lot of injuries for the workers. We're talking serious musculoskeletal issues. And then there's the gear itself. All that dragging and dropping, it causes a ton of friction and impact damage, which means, you guessed it, really expensive repairs.
So, the problem is crystal clear, right? The solution? Well, you engineer your way out of it. The goal was simple. Design a specific tool, a machine that could automate the whole process and take the strain off, well, off of everybody and everything.
And here it is. This is what they came up with. It's a custom belt conveyor designed completely in 3D using CAD software. Now get this machine doesn't actually exist in the real world yet. It's just a super detailed digital blueprint basically, all ready to get put through the ringer in a virtual world.
And this is where things get really, really cool. Think about it. You haven't spent a dime on steel or rubber or anything yet. So how in the world do you know if your design is even strong enough to do the job? Well, the answer is a digital stress test.
The whole engineering process here really boils down to 3 steps. First, you've got the idea, the concept. Then, you build that detailed 3D model we just saw. But the third step, that's the magic one. That's the virtual test, where you can throw all kinds of real-world forces at it to find the weak spots, all before a single piece of metal ever gets cut.
The special tool they use for this is called finite element analysis, or just FEA for short. The absolute easiest way to think about it is like a virtual crash test, but for parts. You can apply all sorts of forces, see where the design might bend, or even where it could break, and you can tweak it and perfect it, all from the safety of your computer screen.
Okay, so the design is pretty much locked in, but now the engineers have a really big choice to make. What material should the actual conveyor belt be made of? So what do? They decide to set up a virtual showdown, a battle royale between 3 different materials to see which one can handle the pressure.
So, let's meet the contenders. In one corner, we've got Nylon 101. You can think of it as the powerhouse, the heavy hitter. Then there's polyethylene, or PE, which is kind of the balanced, more budget-friendly choice. And finally, you've got good old rubber, famous for being flexible. And hey, pay attention to those price tags, because that's going to become super important a little later.
All right, so here are the rules for this little competition. They're going to apply a 1,200 Newton load to each material. That's basically simulating the weight of that 120 kilo oil boom. And they're not just testing one version. They're going to test each one at 3 different thicknesses, 7, 5, and 2 millimeters, to find that perfect sweet spot between strength and cost. So let the virtual games begin.
Okay, the tests are done. Now it's time to sift through all the data from this digital gauntlet and see which material comes out on top. We're going to focus on the results from the 7mm thickness tests because that's where you can really see the differences. First up, the powerhouse, Nylon 101. Just look at this simulation. See that color scale on the right? That shows stress, and the belt is almost totally deep blue. Blue's good. It means very, very low stress. I mean, it barely bent at all. We're talking just over 18 thousandths of a millimeter. That is just incredibly stable. All right, next contender, polyethylene. And you know what? It also did great. Still deep in that happy blue, low-stress zone, totally within all the safety limits. But it did bend about 5 times more than the nylon did. Now, it's still a crazy small amount, don't get me wrong, but that difference, it's worth noting. And now for our final contender, rubber. So technically it was strong enough. It didn't break. But its biggest feature, its flexibility, actually became its biggest weakness here. It stretched more than 1.4 millimeters under the load.
And for a conveyor belt that has to be super stable, that much sagging, well, that could cause some huge problems down the line.
And wow, this chart just lays it all out plain as day. It shows exactly how much each material bent or displaced. Just look at that teeny tiny blue bar for nylon, now compared to the others, especially that huge one for rubber. This visual, it says it all, doesn't it? When it comes to stability, nylon is just playing in a different league. So, the results are in, and the winner is clear. Based on its incredible strength and how little it deformed under all that pressure, the absolute best choice for this tough job is Nylon 101 at 7 millimeters thick.
And hey, don't just take my word for it. That's the exact conclusion from the research paper this is all based on. They wrote that Nylon 101's mix of strength and stability made it, without a doubt, the best pick for any application that needs to be super durable.
But wait a second. What about the price? Remember how nylon was the most expensive one? Well, this is where the story gets another fascinating twist. Sure, polyethylene is cheaper to buy right now, but because it's less durable, you'd have to replace it more often. Nylon costs more up front for sure, but its amazing strength means it's going to last way longer, which actually saves you money over the entire lifetime of the machine.
So you see, this whole digital testing thing didn't just find the strongest material. It found the best value in the long run. And that leaves us with a pretty big question to think about, right? If we can design, test, and perfect the solution to a complicated, dangerous, real-world problem like this, all inside a computer, what other huge challenges can we solve virtually first?